Hi, good morning, good afternoon, good evening to people on the line. We will get started with the webinar in about 2 minutes. We are seeing fantastic response, people joining us from across the world. So let's give it another 2 minutes and then we will kick this off. Thank you. Okay, great. So my name is Rahul Yadav, and I'll be the host for the next 60 minutes. I'm part of the global marketing team for the DuPont electrical infrastructure segment. It's an honor and privilege to kind of be conducting the webinar on transformer needs in wind energy. Wind energy truly happens to be one of the bright spots, right? Even in challenging times. If you look at the current installed base of 650 gigawatts approximately, the growth potential in the industry, it's clear, right? This is an industry that's evergreen. It's truly transforming the energy delivery landscape, and that's creating multiple new technology innovations and business models. So over the course of the next 60 minutes, we hope to hit on some of the aspects that are relevant to the transformer side, and we hope some of the takeaways will be valuable to the team that we have today. Quick note on who we have, right? So just scrolling across the list of participants, we have people from the OEMs, we have people from the operation maintenance, we have the EPCs, we also have certain utilities. So that tells you, right, that this truly is a global call and truly a global opportunity that we are after. The way we want to run is I will introduce our presenter in a minute, but to all participants, you have the options to ask questions via the question tab that you will see on the right hand side of your screen. So you can click that, it will pop out. You can ask questions as you move along. We have a team working in the background to try to reply back to as many questions as they can. And then some of the questions we will also save up for the last 15 minutes, where Eric will kind of take us through the key summary and the key highlights. Let me introduce our presenter, Radek Shevchek. He's part of the Global Technology Organization. He's based out of Poland. 10 years of experience within the Nomex line of business. And prior to Nomex, he really started off as a transformer designer, right? So he really knows his stuff very well, right? So he's worked with Powers, he's worked with ABB, and he also happens to be on the key international working groups for IEC, IEEE, and CGRE. So with that quick intro, I will now hand it over to Radek to take us through the next phase.
Okay, thank you, Rahul. Just one reminder to all the participants: the questions will not be asked on audio. The questions can be posted in the GoToWebinar panel. So whoever can see your panel, it can be minimized or it could be enlarged. So you need to find the field with the questions. When you click on the triangle, it will expand and you just type your question. At the end of the session, we will review the questions and we'll try to answer. I'll try to answer as many questions as possible during this session. So, as Rahul said, the wind energy is definitely the area of interest for DuPont when looking at the electrical infrastructure business, and definitely part interesting for us, for the insulation supplier, are the transformers and the needs for the insulation system. So this presentation will be split in a few parts. I will talk about the wind turbine step-up transformers. I will talk about the trends for increasing size, for repowering, a very important trend for the offshore wind energy. And at the end, I will also talk about the collector transformers, and mainly the offshore collector transformers, which are important part of the system for the wind energy. So to start with, as a background, really, the wind turbine step-up transformers, they became a separate category in the transformer industry after the growth of the wind energy business. And at the beginning, they were used as out-of-shelf transformers, and only then industry learned that there is more and more specific features of these transformers to be addressed in the design, in the operation. So these are not necessarily normal transformers. They work in the step-up operation, increasing the voltage from around 600 volts up to the medium voltage collector system. And originally, they were basically installed on the side of the turbines. And then with the growth of technology, with the focus on the green aspects, on the footprint, on the visible aspects of the visual aspects of the turbines, they started being put inside the turbines. So the thing is that they became smaller and smaller, or they must have been compact size to fit into the towers or into the nacelles. So the thing is that new challenges popped up for the reduced size of the transformers, and also this impacted the ambient temperature of the transformer, because it was not externally to the tower anymore. It was inside the tower when the heat was generated, not only by the transformer but also by the other equipment inside the tower or inside the nacelle. Specific things related to the loading of the transformers, definitely the load of the wind turbine and the transformer consequently is depending on the wind conditions. So these transformers experienced very irregular loading periods during the year, depending on the wind conditions. Very difficult or very specific cyclic loadings, irregular cyclic loadings, and the temperature cycling. So the expansion of the tank was very periodic and irregular comparing to the regular distribution transformer. So there was more and more things identified which are specific to that type of transformers. Definitely the frequent switching, depending on the wind conditions, the transformer could be switched on and off, which increased the inrush current activity in such transformers, and the need for these transformers to be resistant to the inrush currents, and also the harmonics, whether voltage or current harmonics coming from the inverter system in the turbine electrical system. So of course the resistance to vibrations when the transformers are installed are they either in the tower or in the nacelle. And when moving towards the offshore applications, definitely the reliability became critical part because nobody wants to do the maintenance or replacement of the transformers in the offshore installations. So these were the features of the wind turbine step-up transformers, which are important to mention. And whoever is familiar with the Nomex technology for the transformers must be familiar with the slim transformer development that was made in the early years of this century with Powell's, when this concept for the compact transformer using high temperature technology, meaning high temperature solid insulation and high temperature liquids, was developed. So the picture only shows the visualization of how smaller the transformer can be. This is just an example of the 1.5 MVA transformer. And this was really a breakthrough that was a great benefit for the turbine developers, where the transformer could fit in those tight spaces, in the tight spaces of the turbine system. So the example of the characteristic for such transformer, this is based on the typical 2.3 MVA, which was typical the size of the transformer for the 2 megawatt turbine at that time. But the comparison of the conventional transformer and the bioslim transformer, the high temperature transformer, compact transformer with the synthetic ester liquid. It shows the, on the bottom, it shows the temperatures in the transformer. The top oil rise was only increased from 50 to 70. That was 20 degrees increase on the fluid coming from the, going from mineral oil to the ester liquid. But on the winding rise, that was from 55 to 110. So that was like 55 additional degrees on the winding temperature. So that was the space, that was the technology which allowed to compact the size of the transformer. When you look at the weight of these transformers, this specific transformer reduction from 6 tons to 5 tons on the total weight, and the liquid from 1,200 kilograms to 800, that's 50% of the liquid weight reduction. So that was significant impact on the environment, on the weight of the transformer, on the fire aspects. And what is important, although this transformer was very compact, it still maintained the regular losses. So when we have the high temperature transformers, we should calculate losses at higher reference temperature. So it is important that these slim transformers developed for operating at higher temperature. Even this higher temperature did not have an impact on the losses. So for, in terms of efficiency, in terms of meeting today's more and more stringent requirements for the efficiency of transformers, these transformers were still meeting the same requirements for the losses. So that was the slim transformer development. Over the years, the power slim transformers became a mature technology. They became the benchmark for the technology and for the compactness in the transformers. The high temperature technology was adopted by other manufacturers producing similar products, and today many wind turbine manufacturers basically bases their development of the turbines on this compact transformer technology. Synthetic ester liquids became very popular, at least in Europe. The synthetic esters are dominating in the wind turbine transformers, especially in offshore applications where the fire safety and mostly environment is critical. But this is not the only technology. We still see the cast resin transformers used in certain wind turbines by certain manufacturers of the turbines. This is often by the preference of the user. If the end user prefers to have the cast resin technology, there is more trust in the cast resin in terms of the fire performance or the maintenance of such transformers, then cast resin is kind of competing technology for the compact liquid immersed transformers in the wind turbines. Over the years, there was also forced cooling developed for the step-up wind turbine transformers, especially when we have transformers installed in the nacelle, where there is a cooling needed for the generator, for the inverter, for the gearbox. Many wind turbines basically have the integrated cooling system for all the components to be pulled together with one system, which includes the water cooling, and then water cooling also is used for the step-up transformer, and then the size of the cooling system for the transformer itself is not so critical because the cooling system is installed for all the equipment. Definitely, especially in the last years, the energy efficiency is more and more important for the transformers. So the wind turbine transformers have to meet the requirements for the energy efficiency regulations. Officially, the energy efficiency regulations, at least in Europe, do not apply to the offshore installations. So the offshore transformers would not have to comply with the European regulation. But the experience shows that the users of the transformers, they still apply their capitalization of losses, and often the losses in the transformers are even lower compared to the official European regulations for the losses. So the cost of energy may justify going lower with the losses, meaning higher efficiency than prescribed in the regulations. And when looking at the recent developments, we at DuPont, we do not focus only on maximum compactness of the transformers. We know that sometimes the load or the cost optimization may be more critical than the specific size of the transformer. So we look at extending the portfolio of the materials for meeting those more and more fine-tuned designs. So this could lead to the introduction of the materials like the Nomex 926 for the conductor insulation versus Nomex 410, or it could possibly lead to the introduction of Nomex 414 for the layer insulation as compared to Nomex 410 for better and faster impregnation of the material. So we look at those different systems with the industry partners to make sure that we can meet those more and more stringent requirements, but also optimize and fine-tune the designs for the modern transformers. Another range of the products could be related to the temperatures or to the designs, not focusing on the highest available temperatures allowed by the standards, but even finding the intermediate thermal class materials, which could be Nomex 910, which has got Nomex in the name, but this is really a cellulose paper enhanced with the aramid, or we could call it medium temperature class, and not for the extreme temperatures like the slim transformers are, but for the medium temperature designs for the optimized performance and the cost. Thermoplastic materials, that's another area which is in our focus. So maybe soon in the future we will have some materials for that component. Looking at the trends in the wind turbine transformers, definitely the size of the turbines is increasing. I showed this comparison of the 2.3 MVA transformer, the typical steam transformer at the beginning of the development. And when we look at now at the left-hand chart for the onshore wind, the 2.6 MVA, that was, let's say, the average rating of the transformer back in 2018. Since then, definitely the size of the turbines is growing. It's expected that within a couple of years, the average size, not the maximum, the average size of the onshore wind turbines will be like 5.8 megawatt. This is what we see in that chart from the study of IRENA. And definitely for such turbines, 5.8 megawatt, the transformers would be already above 6 mega MVA. So that would be 6 MVA transformers as an average for the onshore installation. So definitely the size of these transformers is growing, and the turbines, and it's even further growing in the offshore applications. In the offshore applications, really the size matters, and the biggest size of the turbines is really appreciated because it allows the big energy yields, while the number of the turbines to be installed and maintained in service can be minimized. So that's why the offshore industry really appreciates the availability of the largest turbines available, and then the largest turbine developments. At the moment, we have the turbines in the range of 12 megawatt with the transformers of around 14, 15 MVA. So these are the small power transformers already, not distribution transformers anymore. So these large turbines are under development. And what is very interesting is that although these turbines are already developed or they are coming to the market very soon, they are not the prime interest of the onshore wind industry. The onshore wind industry does not necessarily focus on those largest ones. Those largest ones are reserved for the offshore industry, while the onshore industry more looks at the improved efficiency, energy yields, fine-tuning of those relatively smaller designs, which are probably more cost-effective as long as they don't have to be used in this critical offshore environment. So that's a trend for the size of the turbines. And then there is interesting trend for the repowering. As we know, the wind energy started a number of years ago, and of course, the best areas for the best wind resources were identified at that time, and the first wind farms were created on those best wind resource areas. with relatively small turbines available at that time. And now when certain areas in certain countries may be saturated with the turbines and there is no more space for the turbines to be installed, the thinking is why don't we replace those smaller turbines with the bigger ones, giving better energy yield, also being more energy efficient. And that's why we talk about the trend of repowering, where the old smaller turbines are replaced or being replaced with the bigger, more efficient turbines. So what is interesting, there is no need then to look for the social acceptance, because the wind farms are already there. So there is no need to ask for permission to install the new turbines, because they are there anyway for a number of years. It's just a replacement for the bigger one, maybe more silent even. Some of the turbines may be getting to the end of life. They were originally designed for the 20 years of life, so some of them may be already obsolete, whether for the technology used or basically materials are at the end of life. So that's why this trend of repowering, replacing the turbines with the newer and bigger ones is important. So in onshore, at least in Europe, in onshore, it may be the main trend for the developments, that the old turbines are replaced with the new ones. Sometimes it may not be the complete turbine. Sometimes the under base, the foundation stays the same as much as possible. So sometimes only the components are replaced and not the complete turbines. Just to give an idea about the North American market, it's estimated that in 2030, that 25% of the turbines installed will be at the end of their life. So there will be natural replacement needed because of the age of the components or the age of the equipment used. In Europe, of course, the first countries and the first developments in the wind industry, the massive developments, we started in Denmark, Germany, UK. So these are the key markets for the repowering. And then moving to the most interesting trend for us at the moment is moving to the trend of offshore wind. This interesting map from the brochure Ørsted shows nicely the areas which use the offshore wind industry now. So there's in Europe, this is mainly the North Sea. Some areas in the US East Coast and some areas in Asia, but definitely there is a huge potential for exploring more areas for getting the green energy from the offshore location. So at least in Europe, the estimations based on the recent data and the recent strategy developed in Europe is that now in 2020 there is like 22 gigawatts of energy installed offshore, while in 2030, 10 years from now, it's going to be almost multiplied by 5 times. Still focusing on the North Sea and Baltic Sea, which is the best wind resource, but in 10 years it may be multiplied by 5, and in 2050 that could be multiplied another 4 times. So there is a huge potential identified in Europe, mainly in the North Sea, Atlantic coast, Baltic Sea, while the other regions, of course, they will also develop the offshore wind capabilities. Again, to remind and emphasize the growing size of the turbines. This may be more visual comparing to the Statue of Liberty or the Eiffel Tower. Yeah, this is really the impressive growth in the size of the turbines, and they are bigger than those used in the onshore industry. So when moving to the actual equipment, because of the size and because of the investment needed for the development and the know-how needed for the development of the biggest turbines, there is not so many players at the moment. In Europe, we can identify the 3 key players which are shown on the slide. So that would be MHI Vestas, that would be Siemens Gamesa, that would be GE. These are the 3 leaders, and you can even see that for Vestas, who was the long years leader of the wind industry, it's not Vestas only. It's a joint venture with Mitsubishi Heavy Industries. Siemens joined the forces with Gamesa for development of the offshore turbine. So this shows the investments, the know-how, the expertise needed for development of these turbines. And until recently, the GE was the record holder for the size of the turbine. They had the 12 megawatt Haliade X turbine available, while it was only a couple of weeks or maybe a couple of months ago when Siemens announced availability of the 14 megawatt turbine. So it was announced now. Probably the first unit would be available next year for installation. So this is the race for the largest turbines. And one very interesting trend, whenever the larger turbine is available, this is becoming the main focus for the new investors. If somebody is planning to install the turbine, to install the new wind farm in 3 years from now, the orders for these largest turbines are placed immediately. We could call it, this is buying green bananas. This is only a prototype at this stage. The turbine will be only available next year, but definitely people are interested to have these largest turbines when they set up their wind farm in 3 years from now. They don't want to wait for the development in 3 years from now. They want to buy the largest turbines available today. And what was mentioned, the technology for compact transformers, the technology based on the aramid insulation materials became mature, became kind of standard and benchmark for the wind turbine step-up transformers. And this is the case also for all these leaders which are shown here on the slide. The high temperature transformers are in the specification of Siemens Gamesa. We know also that the transformers for MHI Vestas, they also use the aramid paper for ensuring the reliability and the extended life of the equipment. GE also uses the transformers with aramid insulation. So all these leaders of the largest offshore turbines, they trust the technology of DuPont Nomex for the development of the transformers, which are important components of these turbines. And when looking a bit at the details of these large offshore wind turbine transformers, I mentioned before, they are not distribution transformers anymore. They are more small power transformers in the size of more than 10 MVA, now going beyond 15 MVA. The standard voltage in the offshore collector system becomes the 66 kilovolt. There are even some discussions or the considerations for 130 kilovolt class, but now the 66 kilovolt is becoming the standard. And because of that, again, these are more small power transformers than distribution. And this drives the design of the transformers. This drives the components needed for the transformers, but it also means the shift in the producers of the transformers. So before, it was really the distribution transformer producers who supplied the transformers for the step-up applications, while now we talk more about the small power transformers. So even within the largest multinational companies, that the product is moving from one plant to another. It's not distribution transformer plant anymore, but new developments are more in the small power transformer factories. And again, the liquids, the synthetic ester liquids, at least from my European experience, the synthetic ester liquids dominate the application in the step-up transformers, whether it's onshore or offshore. Not much experience or acceptance for the natural esters in Europe because of the temperature conditions. So there is more trust in the synthetic esters because of the low temperature performance. Still, these transformers trust the high temperature insulation materials like DuPont Nomex. The transformers are still, or the high temperature transformers are still important cost component of the turbine. but still the performance provided, the reliability and the compactness of the transformers still is a trusted solution, and still these transformers are used and considered as a base for the newest developments. I mentioned the green bananas. What is important, of course, with the limited number of the key players in the developments for the offshore, definitely they look at the global supply chains for the components, because when the global projects are built by the, let's say, European or American suppliers, they look for the global supply chain to be able to make the turbines and all the components whenever is needed in the world, which also drives the push for the local contents. Sometimes the components of the transformers or the complete transformers are made locally to ensure that when the country like Taiwan now is looking at the development of the new wind farm offshore, the local industry would get some benefit from producing the components for these new developments, new wind farms. And this is an example of the state-of-the-art offshore transformer. This is the case of ABB Windstar transformer, which is a ABB proposal for the offshore wind turbine applications. Again, available in 33 kilovolt and 66 kilovolt, but standard, or the industry standard, is really moving towards the 66. And there is number of features listed here. This is coming from the ABB brochure promoting this type of transformer. And I highlighted with the red dots. The red dots are mine. I'm highlighting number of features which are in line with the features provided by Nomex insulation. So when we talk about the best-in-class solution for variable loading and typical extreme environmental events, definitely the state-of-the-art insulation materials help in surviving them. Optimized weight to lower wind turbine structural costs. That's again compactness of the transformer related to the Nomex insulation. Long life or extended life and the guaranteed loadability for 30 years. So these are the features which ABB promotes for their transformers, and I really identify the same features to be proposed by the Nomex insulation. So definitely the state-of-the-art insulation materials can be and should be the integral part of such state-of-the-art technical solutions offered for these large offshore wind turbine transformers. So this was just an example of the features promoted by ABB for their transformers, but I really support and agree that this should be the features of each large offshore wind turbine transformer. What is interesting when talking about the optimization, in the past, the optimization of the slim transformer for installation inside the tower was related to the size of the tower. And now when we talk about the offshore installations, we have even more complex installation structure with the foundation in the seabed, then the transition piece going above the water. And all these components are dependent on the weight of the total wind turbine. So we can imagine that minimizing the weight of the entire turbine and minimizing the weight of the electrical equipment inside will definitely have impact on the supporting structure and the cost of this supporting structure. So that's why this is again from the interesting brochure from Ørsted about this is confirming that minimizing the cost of minimizing the weight, minimizing the weight of the total installation above the sea level definitely has an impact on the cost of the supporting structure. So this is important part of the modern optimizing of the cost of the offshore installations. And this is another aspect of of the offshore installations. The interesting chart from Irina shows the size of the turbines. This is the size of the bubble, the size of the turbines, and the distance from the shore or the depth of the coast of the seabed. And you can see here that many wind farms with the growing size may go far in the from the shore. The distance exceeds 140 kilometers, but the depth is rather below 50 meters. If there are some wind farms which are installed on the deeper water, they are relatively close to the shore, less than 20 kilometers. So there is kind of a borderline which could identify the today feasibility of installing the turbines offshore. And that's why there is bigger and bigger interest for the offshore installations with the floating structures, where the depth of the sea or the distance from the sea may be less critical. So there are new developments for the turbines to be installed on the floating structures, or maybe I should say not really the turbines, because the turbines could be the same. The turbines may stay the same. It's just the supporting structures which are under development. And here again, the lighter structure on the top we would have, the cheaper the supporting or the cheaper floating structure would be in this case. So definitely there will be trend visible for optimizing the weight of the floating turbines for reducing the size and cost of the supporting floating structure. And there is a very interesting trend which was identified that installing the turbines or installing any wind farm components onshore is very difficult. It requires the window for the weather. It requires very specialized equipment for cranes and specialized teams, crews for doing these offshore jobs. While when developing the offshore systems, what was realized was that all these works, or majority of works for assembling the components like the turbine or even the collector substation, could be done in the harbor. So there is no need for the weather window. There is no need for specialized crews and equipment to work far offshore. All this could be done in the harbor, in the more controlled environment, and only when everything is ready, it would be pulled to the deeper waters. So this indicates very interesting opportunity for the floating structures, that they may at certain stage become even cheaper than installing the fixed structures, because majority of the work could be done in harbors, and then complete equipment could be pulled outside. And of course, these floating structures, they are not much. At certain cases, there could be a choice between fixed installation or the floating structure, but in certain cases, like the west coast of US or Hawaii or Japan, where there is no shallow waters, this is no-brainer. If there is a development for the offshore wind, that would have to be the floating system. And then further staying with the offshore industry, definitely the wind turbine and the step-up wind turbine transformer is not the only component. The collector transformer is another important part. And of course, the collector transformers also exist in the onshore installations. They may not be so critical. There is probably not much focus on the special developments for the collector transformers for the onshore wind farms. But in case of offshore, definitely this is very critical piece of equipment. Like you can see on the chart, entire substation with the heavy transformers inside on the onshore. And this is one of the critical components for the wind farm connection to the grid. And if the distance is long enough, if the power is long enough, this platform may not be limited to the AC collector and the transmission transformer, but could extend to the HVDC link. And then we have the HVDC converter transformers to be involved in the installation. So moving quickly to this collector substations or the transformers, typically on the substations we have at least 2 transformers in parallel. This is for redundancy. And if one transformer goes down, the operator does not lose complete wind farm. The second transformer could take the load and the power would be still available. Today, these transformers may vary from 100 MVA to 400 MVA, going up to 400 kilovolt, but always at least 2 transformers installed when the safety and the reliability is the critical component. And again, here we can talk about this need for the optimization. The lighter the substation would be, the cheaper the supporting structure would be. And here the case from the or the suggestion for the optimization opportunity from the ABB publication about the offshore collector transformer. When you see this interesting load pattern or the loading pattern during the year, it was only 10% of the year when the transformer, on this example, it was only 10% of the year when transformer was fully loaded. When the transformer was fully loaded, and the rest of the year that was like 80%, 60, almost half of the year that was like less than 20% of the load on this transformer. So of course, one of the optimizing principle could be derating this transformer instead of matching the power of the transformer with the total installed power of the wind turbines, going down with the power rating of the transformer. This is what the picture on the right-hand side shows, where the transformer rating was selected to 80% of the total installed power of the wind turbines. And then you would see that over this 10% of the year, 10% duration, the transformer would be overloaded or could be overloaded, while still it would be relatively low loading on the transformer for the remaining of the year. So that optimizing of the transformer size, the transformer electrical size to the actual load pattern could be very important tool for optimizing the size, the weight, and the cost of the offshore collector transformer. And definitely, the farther we can go down with the size of the transformer, the farther the bigger overload we can allow for this short period of the year, the more we can optimize the size of the offshore transformer. So again, that's based on the study proposed by ABB in Spain for the offshore transformer. And getting close to the end here, when talking about the growing size of the wind farms, which of course would impact the requirements for the collector transformers. The left-hand chart shows again the chart from IRENA about the wind farm size. This is the size of the bubble on the chart, and the turbine size. So with the years, the wind farms started from the small bubbles. Over the years, they grew to the bigger bubbles, and of course, the size of the turbines was growing as well. And then we have this latest development announced for Vattenfall's Polance Kust wind farm to be installed operational in 2023, so 3 years from now. It's going to be 1.5 gigawatt capacity. So I proposed the new bubble on the chart, which really shows the further growing size of the wind farms, the growing size of the turbines, because that would be 11 megawatt turbines, 140 units installed in this wind farm. So it really shows the trend. It really confirms the trend of the growing size of the turbines. It really confirms the trend of using the biggest available turbines for the offshore installations. And the pictures on the right, on the top right, this shows also the trend. Before, historically, the collector substations were designed for collecting the power from the entire wind farm and transferring the power to the coast. while now we can see this growing size of the turbine. So there may be a few collector substations, there may be a HVDC link depending on the distance from the shore. And what is interesting, if such huge wind farms are installed in between the countries, on the seas between the countries, the connection or the transmission lines may be also used as an international overseas link. So independent from the energy generation from the wind, the links may be used as international links for transferring the power between the countries. That would be so-called hybrid systems for the transmission. And I mentioned the HVDC. This is a chart from the SIGRE brochure on HVDC. The HVDC may be important if the size and the distance from the shore is growing. So if the distance is relatively small, we could have relatively cheap AC system for collector, but the cables would be more expensive. And with the growing distance, the size or the cost of the cables would be dominant. If we have HVDC, we have relatively cost for the HVDC link in terms of the substations, but the cables would be cheaper. So there is a break-even distance. This is considered between like 50 or 100 kilometers, where the HVDC could be more cost-effective comparing to AC systems. And really, we are getting to the summary. So to summarize very quickly, the wind turbine step-up transformers are not regular distribution transformers. They are special. They require special solutions, and they are not distribution transformers anymore. They are moving towards the small power transformer size above 10 MVA with the voltage class 66 kilovolt today. The offshore wind industry is very important trend and growing fast, which presents big challenges, but also big potential for further development and opportunities for the state-of-the-art technologies. And we cannot forget about the offshore collector transformers with possibly HVDC applications if we look at the future developments for the offshore wind industry. And last but not least, some adjacent opportunities as well, not 100% related to the wind industry, but as the wind farm developers look at the green impacts or the minimizing the impact on the environment, there is more and more common to use the electric vessels for servicing and maintenance of the turbines. So definitely the need for charging stations for these electric vessels, which is kind of adjacent opportunity related to the wind energy. So this concludes my presentation. I hope the audio was okay and you could follow the slides properly. So now I will try to see what questions were collected during when I was speaking, and see what questions I could answer for you for the remaining time of this session. So let me see at the collection of the questions and what could be the interesting ones to address here. So here is the question: why only synthetic ester dominating the slim trafo, while in the market there are also natural esters that have high temperature performance and high flammability? The reason for synthetic esters, at least in Europe, was the need for installing the offshore the wind turbine transformers in the areas which are not necessarily always warm. So in the cold climate, there was no trust in the performance, in the low temperature performance of the natural esters. So that's why in Europe, synthetic esters, originally silicon liquids, but then synthetic esters were dominating for that application. Another question, normally building a transformer with high temperature design would need many complicated and shaped parts. We have not seen these shaped parts available in Nomex. How can DuPont support in this aspect? This is something which we see definitely, and we will address this trend, and we are already addressing. It's getting more and more interest in designing and use and development of the high temperature power transformers, not only related to the wind turbine applications, also to the power applications, while historically the full high temperature solutions were reserved for the distribution transformers, extending to the wind turbine transformers and traction transformers. In the power transformers, we talked more about hybrid designs where the Nomex insulation was combined with the cellulose. Now, with the growing interest in the high temperature power transformers and definitely high temperature growing size of the wind turbine transformers, we are getting ready to supply this type of component. We are in the development, or actually we already commercialized the wet formable Nomex board for shaping the high voltage and insulation part. So now the angle rings can be available, and the snout, the lead exits can be now formed from the wet material, similar to what was available so far with the cellulose components. So now we are getting ready, or I should say we are ready today to provide this type of components. We are just working on making these components available globally and not being limited to the specific regions for availability of these components. What are our interesting questions? Okay. Here is the next question. As size of the turbine increase, what is the impact of vibrations on transformer designs? I'm not so sure that the size of the turbine would have the impact on the vibration. Definitely the location of the transformer has that impact, because the transformer installed in the nacelle would have the impact. If it's in the nacelle, there would be more vibration than in the tower. I'm not so sure if the size of the turbine would also involve would also increase the impact on the vibration. Next question. What is the insulation level of transformer in offshore? As I said, traditionally it was 33 kilovolt class. Now it's moving to 66 kilovolt class. So depending on the standards, whether this is IEC or IEEE or any other regional standards, the insulation level would be selected based on this. But 66 kilovolt as a rated voltage becomes the standard for the offshore, with the further considerations for 130 kilovolt class. Next question. Beside ABB, who are the main actors to speak with that are working on innovative new projects with Nomex? Yeah, definitely ABB is one of the leaders in the transformer industry globally. So they have great developments for the offshore transformers, but in general, at least in Europe, when we stay in touch with the transformer suppliers, all the main producers of the transformers have adequate developments for the offshore industry. So I mentioned the traditional Power Slim. Now the heritage from Powers is the CG power systems. with the factory based in Ireland. So they work on the developments for the offshore industry. Other leaders of the transformer industry, they also have solutions for the offshore wind. I'm looking at the clock here. Maybe one more questions. Are there tools to monitor these compact transformers using Nomex 926 or Nomex 910? Example DGA. Yeah, there were some studies done in the past, and we have some materials, some technical articles available for addressing what is the gassing and the gassing behavior and the DGA for the high temperature insulated transformers. So there are some references mainly for the hybrid power transformers, because these are mainly the power transformers are monitored for the DGA. There may be less record for the step-up transformers because of the size. They are less frequently monitored for the DGA, and if they are, this is normally in the discretion of the operator of the wind farm to keep this data. It's not always easy, or I should say impossible, to get details of such analysis or such measurements to have available. If it comes to the Nomex 910, which is the cellulose paper combined with the aramid, the analysis should be easier because this paper is mainly cellulose, so it would be easier, or it would follow patterns more typical for the typical insulation system based on the cellulose. I see many other questions coming. I'm afraid we are getting to the end of the time. I think what we will do, we will try to answer those questions directly to people who ask those questions, so that you don't stay with the question unanswered. We will try to address these questions, and I'm afraid we are getting to an end of the time. I'm glad to see these questions, because this means that the topic was interesting, and I hope it was really informative for the audience and well received. Rahul, are you there to conclude?
Perfect. Thank you, Radek, I think, for an engaging discussion. And I think we could gauge by the number of questions that we had that this truly was a topic that garnered a lot of interest. So to people who joined us, a big thanks. And for more information, feel free to log into our website, ei.nomex.com, or follow us on our LinkedIn. Right at the end of the webinar, you will receive a feedback form. So that would be another opportunity for you to take note of Radek's contact details, and also ask our team any additional questions that you may have. And just to repeat what Radek said, there are multiple questions which we could not answer today. So our team will reach out to you and try to get the answers as soon as possible. So once again, thank you. Stay safe wherever you are, and have a good rest of the day. So we'll wrap up. Thanks, Radek.
Thank you.